Okay, so this course, I'm gonna introduce the SN diagram. Okay, so we have to evaluate the stress life by the fatigue failure criteria, and these components might be subjecting to the fluctuating stress or the completely reverse stress. And I will just define what is the completely reverse stress is. Okay. And of course, there's the important parameters are endurance limits. Okay, so it's the crucial factors to design the fatigue life. Okay, so basically we used to evaluate this component fail or not by depends on the parts operation, right? So during the operation, the force might be developing, right? And the stress will concentrated. The stress concentration increases during this parts operation, and then the stress increase. Okay. So, however, this is not a real case that we design the fatigue life. Okay, so we don't much care about how the parts operating because we only care about the allowable maximum stress and the fatigue stress. So based on the endurance limits, okay, based on the endurance limit. So we plot this SN diagram based on the number of cycle, the N number, okay, based on the number of cycles and the fatigue stress that can be compared against the constant nominal stress. Okay, constant nominal stress. Okay, so there are different stress situations. The fatigue stress or the cyclic loading. Okay, so now we have to define some terminology of those stress. The first is the mean stress. So which is the equals to the maximum stress plus the minimum stress divided by 2, right? So it's the mean stress. Okay. So for example, there's a rotating shaft with the two supports. Okay, and there's the a point load applied at point A. Okay, so during this rotating shaft, so the point A might subjecting to the tension or the compression. Okay, tension or compression, right? So when this rotating with the 180 degrees, so the point A will feel compression, right? And in the case if this minimum stress equals to zero, the second case of the constant amplitude loading. Okay, the second case is that the minimum stress is zero. Okay, the minimum stress is zero. Okay, and the third case is that the mean stress equals to zero. Okay, the mean stress equals to zero. Therefore, the maximum stress will equal to the absolute value of the minimum stress. And we call this the amplitude loading is the complete reverse stress noted by the sigma AR. The completely reverse stress means the mean stress equals to zero. Okay, the mean stress equals to zero. Okay. Okay, so what I mentioned previously for this the case with the point A, it will feel tension and compression, right, during the rotation in 180 degree, right? And then if for this real experimental setup, there's the support and the load applied to this fatigue test sample. Okay, and then we can plot the shear and the moment diagram. Okay, and for this moment diagram, there's a constant maximum moment region. Okay, and then it can be we can use it to calculate this normal stress, or say the maximum normal stress, the mean maximum normal stress. Okay, so equals to my over I. So we can calculate this the maximum stress, right? Okay, so by the experiment, remember those fatigue criteria mostly is based on experimental data. Okay, so for SN diagram, okay, we do the experiment with the fatigue test, right? So the previous page, so we do the experiment here. Okay, this is what the experiment setup is. Okay, and we do this experiment. We collect those data with different cycle, with a different loading cycle. Okay, so we can collect those experimental points. Okay, okay, corresponding to its fatigue strength, or say the failure, the fracture strength. Okay, so when this the fatigue strength reach a constant, which is called the endurance limit, which is called endurance limit. That means based on the design of the based on the fatigue life. If we design this component with infinite life, okay, ideally, if this fatigue strength is below the endurance limits, this fatigue components will have the infinite life, right? Ideally. Okay, therefore, we can run the different components, different with the different materials. So we can plot the various the SN diagram corresponding to the material. Okay. Okay, and then we define the F vector. I'm gonna introduce what is this F vector is later. Okay, so for this SN diagram, we define the limits of the fracture stress as the ultimate tensile stress. And there's a reflected point, which is a parameter F times the ultimate tensile stress. Okay, so for this cycle, one cycle, which is represent the static loading, right? Static loading. So we just assume the limit of this static loading as the ultimate tensile stress. And there's a reflected point here, which is the F parameter times the ultimate tensile stress. Okay, and there's the linear relation, right? There's a linear relation. Okay, and from experiment, the previous page, right? So we do a lot of experiments. We collect those data, and we plot this the F function corresponding to the ultimate tensile stress. Okay. Okay, so we collect those figures. Okay. So between this reflect point to the endurance limits, right? So this point is the reflected point, the SUT, ultimate tensile stress times the factor of the f function, and this point is the endurance limit, right? So between them, which is the linear function, right? And we define this cycle is higher than the 10 to the power of 3, which is the high cycle region. And below that is the low cycle region. Okay, so we can find this linear relation because we just define it as a function of y equals to mx plus b, right? And y is the log of the fatigue stress. Okay, m is the slope and the b is the intercept. Right? And the x is the log of the number of cycles. Right? So, and then we can just manipulate and play with it, and we find a linear relation between the high cycle region and the endurance limit within this region. Right? It's a linear. Okay, and then we can define that m is a constant b, and the exponential b is the constant a. Therefore, we define the linear region between the high cycle and the induced limit, which can be represented as the SF. The fatigue strength equals to A times the N is the number of cycle power of the B. Okay, and then we, as what I mentioned previously, those fatigue properties mostly is based on experimental data. Okay, so we can run this experiment with the tensile strength, the ultimate tensile strength corresponding to its endurance limits. Right, so we do the fatigue test as what I mentioned previously. We have the shaft with two supports and we apply a force and keep rotating that. Okay, so we find the endurance limit with the different materials like carbon steel, alloy steel, or the wrought iron. Okay, so we can plot the chart of its endurance limit with respect to its ultimate tensile stress. Okay, so we have to notice that the unprime simple SE indicates the endurance limits of the actual machine element subjecting to any kind of loading. And the SE prime, which is the endurance limits estimated by the rotating beam itself. That means the SE prime is the endurance limit from experimental data from the previous experiment that I mentioned, right? So we have the beam keep rotating that, right? So that's the ideal experimental data. For the SE prime, that we have to take into account many vectors, like the surface vectors or the geometric vectors. And for the SE prime, we only have to consider which is the rotating shaft only. Okay? Okay, so usually the SE prime, okay, the rotating beam or rotating shaft equals to 0.5 SUT, 0.5 times the ultimate tensile stress. Okay, based on the design point of view, okay, just evaluate, okay, estimate the SE prime equals to 0.5 SUT. Okay? Okay, so as what I mentioned, right? So we have the high cycle point here or reflected point here and this endurance limit here, right? And this point can be defined by the F function times F factor times the ultimate tensile stress, right? And then we can do a calculation by the this F times SUT, right? Equals to A as the SF equals to ANB, right? So for the SF, can be defined as the F times the SUT equals to A times the number of cycle equals to 10 to the power of 3, right? Okay, so and then we can plug this SF. We can use the endurance limit, right? We can place it in the this fatigue strength here, and the number of cycle equals to 10 to the power of 6, right? And then we divide it with each other. We can divide it. It's two equations, right? We divide it. It's two equations, right? And we get we can manipulate that, and we can get this relation, right? Okay, so we can find the parameter B, right, equals to a function of SUT, F, and endurance limit. Okay, and the similar process, we can square the SF, which can be represented as the F times the SUT. Okay, and square and divided by the same divided by the SE equals to A times the 10 to the power of 6 and power of the B, right? So we can get the function, the expression of the A constant, okay, in A per meter. So we got A and B. Okay, got A and B, right? Okay, so we can replace the SF by using the completely reverse stress. Completely reverse stress. That's most of the case. The problem will tells you. Okay, and we know that the parameter A here and B here, and then we can find the number of cycles. Okay, so remember that for this SN diagram, it can be used only in the completely reversed stress. That means the mean stress equals to 0. The mean stress equals to 0. Okay. So there's one example for this 1020 steel. For its materials property database, the SUT, the ultimate tensile stress, equals to 70 KSI, which is subjected to the completely reversed stress, 45 KSI. And the first question is that the safety vector for the number of cycle equals to 10 to the power 4. And the second question is that how many cycles before it failed. Okay, before it failed. Okay, so for the endurance limits, it can be estimated by the 0.5 times the SUT, right? So the endurance limit is 35 KSI. And F vector, we can check the table, right? So when this SUT equals to 70, so this F vector, well, it's around like 0.9. Okay, so we can get the parameter A, right? The 0.9 times the SUT divided by 35. So the A constant equals to 113.4 KSI, right? And similarly, we can find the constant B, right, equals to minus 0.0851, right? And the linear relation between the high cycle point and endurance limits. Okay, so we can plot the constant A and constant B with the number of cycle that the question tells us is the 10 power of 4, right? So the fatigue strength can be calculated. That is equals to 51.8 KSI, right? And the safety factor equals to the fatigue stress divided by the completely reversed stress equals to 1.15. Okay, 1.15. Okay. And the second question is that how many cycles it's gonna fail, right? It's gonna fail. Okay, so for this SUT is for 70 KSI for this high cycle point right here is 36 KSI. For this endurance limit right here is 35 KSI, right? So for this, the first question is that we ask when this number of cycle equals to 10 to power of 4, right? What is its safety vector is, right? So for this, right, for this previous page, we asked when this cycles equals to the power 10 power 4, what safety vector is, right? It's about 1.15, right? Okay, and also the questions already tells us it's completely reversible stress equals to 45 KSI. Okay, so this the current states will locate at this point, right? So this number of cycle 10 to power 4 and the completely reverse stress, right? But this second question asks, what's the number of cycle when it failed? Okay, when this rotating shaft fail. Okay, so this completely reversible stress is the same as the first question, right? So this stress remain, right? And this number of cycle keep increasing until it fail, until it touch this linear function. So we can find this number of cycles. The cycles that this rotating beam will fail under this completely reversible stress, 45 KSI. Okay, so we can go back to the equation of this number of cycles, right? So we use the completely reversible stress, right, divided by the constant A, part of the inverse of the constant B. Okay, so we can get the number of cycle equals to about the 52,000 cycles. This rotating beam will fail. It will fail. Okay, so next we're gonna consider more factors. If this beam or this rotating shaft, well, it's not just a rotating beam. Okay, so maybe this shaft, this beam, has the surface defect or surface stress concentration, or its size. Okay, so maybe it's not the wrong shaft and the different loading, or this rotating beam is subjecting to the this fatigue test under different temperature, and what's the requirement of the reliability that we have to take into account, right? So for the SN diagram, previously we used the SE prom, right? So that's mean we got this endurance limit only from the rotating beam test. But now we have to consider other vectors that will affect those endurance limits. Okay. So these endurance limits will change, right? But it's not the SE prom only. It's not the SE prom only. Okay, so we have to consider the surface, imperfection, the size, shape, dimension, loading type, or temperature, right? So for this fatigue test, it's only the rotating. However, for the real case, it may be not just the rotating, it may be the bending or the axial loading, tension, compression, and so on. Of course, there are more complicated factors that we can consider, okay, like the corrosion or electroplating or the frequency, cyclic frequency, and so on, okay? But for this chapter, we're gonna just focus on the few factors, okay, few modification factors. And these factors can be called as the marine vector, okay, marine vector. Okay, so right now we're gonna use the new endurance limit to replace the SE prom, okay? Replace the SE prom. Okay, so we define the SE, which is the endurance limit, take into account the different marine vectors, and the SE prom is the endurance limit evaluate by only the rotating beam, only for the rotating fatigue test. So here the Ka is the surface vector, Kb size vector, Kc loading vector, Kd the temperature vector, Ke reliability vector, and so on. Okay. Okay, so for this surface vector, the endurance limits equals to the Ka times the Se prom, which is not the case of the maximum stress equals to the stretch concentration max times nominal stress. Okay, because we are focus on the fatigue, the cyclic loading, okay, but not the static loading. Okay. So again, based on the experimental data, right, as what I mentioned, while the fatigue criteria analysis mostly based on the experimental data, right? So the Ka corresponding to the ultimate tensile stress with the different materials or the different manufacturing process, right? We can get a different curve between the SUT and the surface vector. Okay, surface vector. Okay, and the Ka can be obtained by fitting the part curve. Okay, can fitting those curve. Okay, we can fit in those curve together the part curve of the Ka and the SUT. Okay. Okay, so we got this fitting curve, right? The fitting curve corresponding to the different materials or the manufacturing method, right? So we can get the factor A and the exponent B. Okay. Okay, the second is the marine vector is the size vectors. Basically, maybe this is not only for a wrong rotating beam. Okay, so if it is not a wrong rotating beam, we have to consider the size vector. Okay, that's mean we have to consider the cross section, or say the area, cross section area. Okay, that is the area when the 95% of the maximum stress occur. Okay, so we have to define a diameter called the equivalent diameter DE, which is the diameter that's the area, not the area, when the 95% of the maximum stress occur. Okay, so we define this parameters DE. For example, for if this beam is the rectangular but not the round shape, it's a rectangular. Okay, we define its equilibrium diameter is equal to 0.808 square root of the h times b. Or if this cross section of the this beam is the I beam, okay, so we can define its equilibrium diameter equals to 0.05 b times a, okay. Okay, therefore, if those DE within this area with the different, the DE range, okay, so you can define a KB corresponding to the different range of the equilibrium diameter, okay, equilibrium diameter. Okay. And the third vector is the loading vector. As what I mentioned, if this spaceman, the shaft or beam, which is not only subjecting to rotating, it may be bending or axial loading. Okay. So the test spaceman is not is only subjected to bending. We can define the KC, the loading vector, equal to 1. If it is not, maybe this beam, this spaceman is subjecting to the axial loading, tension, compression, and this KC vector equals to 0.85. Okay, 0.85. Okay, and if this shaft is under torsion, you can define the KC equal to 0.51. Okay, and in practical case, if this spaceman with a torsion stress only, you can define the von Mises stress equals to 0.577 times the shear stress. Okay, the shear stress. Okay, so the normal case, this spaceman is not only bending, it might be axial torsion applied to it simultaneously. Okay, and the alternative ways that we can define the KC equals to 1 and the stress by using the von Mises stress. Okay, by evaluating by the von Mises stress. Okay, the fourth marine vector is called the temperature vector, KD. Okay, so if this spaceman is operating at high temperature or low temperature, so if this spaceman operating at low temperature, that means its SUT will increase and the induced limits increase also. And when this temperature raised, that means this spaceman might have this the creep, right, phenomena and oxidation, right, during this operation at elevated temperature. Okay, therefore at low temperature, I mean, its ductility decrease, right? For the high temperature, its ductility or toughness increase in generally, right? So we can define some parameters like the ST, which presents the SUT at operating temperature, and SRT defined as the SUT operating at the room temperature. And the KD vector equals to ST divided by the SRT. Okay, so we can get the two approximate equation based on the different unit, Fahrenheit or Celsius. Okay, and you need the ST to find the F vectors. And if you use the ST to find SE prime, and you don't need to use the KD vector anymore. I will explain this later. Okay, I'll explain this later. Okay, the fifth marine vector is called the reliability vector. Okay, so if we just need the reliability is the 50%, and the reliability vector KE equals to 1. Okay, we can plot this distribution, normal distribution or Weibull distribution corresponding to 8% standard deviation. Okay, so if we need a higher reliability, if we need higher, for example, we do an experiment, right? We can find this endurance limits corresponding to the different sample, right? Different specimen. Okay, so if we just wanted the 50% of the sample is okay. It's okay. So the KE vector equals to 1. Okay, so this half, if we just need 50% of the reliability corresponding to the endurance stress, endurance limit, right? Well, that's KE vector is equal to 1. Okay, so if we test the higher number of the specimen, and we need the higher reliability, for example, 95%. Okay, and this KE vector will decrease to the 0.868. Okay, if we need a higher and a higher reliability, this KE vector will decrease, right? Will decrease. Okay, and the 99% means the 99% confidence of the specimen or sample has the endurance that we calculate. Okay, so we test the one sample. Okay, so it's meets the endurance limit that we calculate. We test the two samples. Okay, the SE meet the required meet that we calculate. Okay, we need to reach the 99%. That's the sample's endurance limits we calculate. Okay, so there's one examples here. For example, we have the rectangular beam with the dimension 1/2 inch. Okay, 1/2 inch. It's a steel bar, and its ultimate tensile stress equals to 123.6 KSI, which is subjecting to the completely reverse axial loading. Okay, and it's operating at the temperature 580 Fahrenheit. Okay, of course, the SUT is related to the temperature, and we require the reliability 99%. And what's the fatigue strength for 50,000 cycles? And what are the F factors? What is the endurance limit, SE? And what is the SE prime? Okay, so we can find the KT vector, the temperature vector, right? The ST divided by the SRT, right? So we got the KT vector equals to the 0.971. okay, based on the Fahrenheit. Okay, so the ST equals to the KD times the SRT equals to 120 KSI. So following calculation, we're going to base on the 120 KSI. Okay. So now we just use the SUT equals to 120, but not 123. In this case, we don't have to consider the KD vector anymore. Okay. So with 120 at this first cycle, this static loading limit here, and we find its F vector equals to 0.82, right? Okay. So we can find the high cycle region right here. It's equals to the 98.4. Okay. So if we use the S80 at the operating temperature, so we don't have to consider the KD vector anymore because the KD equals to 1 in this case. Okay, so it's like if the SE prime equals to the 0.5 times the 123.6, right, equal to 61.8, and 61.8 times the KD vector equals to 60 KSI. Okay, so in this case, it is by using the 120 KSI instead of the given 123.6 KSI. Okay, so the F factor we already find is the 0.82, and the reflected the high cycle point is 98.4, and the SE equals to the marine vector times the SE prime. And SE prime is a function of the SSUT equals to 60 KSI. So these two values are the same, right? Are the same. It's based on what's the ST you use it. You use the 120 or 123. Well, okay, so first is the KA, the surface vector, right? So for this questions, it's a steer ball, right? Okay, it's a steer ball. Okay, and it's hollow and lateral as machine. Okay, it's machine. Okay, so we find it's the we say the weakest manufacturing method. Okay, so the machine manufacturing method will not enhance its strength. Okay, because we just cut, just slice those materials without any strength hardening, without any strength hardening. So we have the we can find this machine, right? Spaceman, and corresponding to its the KSI here equals to 2, and the A vector equals to 2, right? Based on the KSI units. And the A equals to 3.004 if we use the make-up part. Okay, and the exponent equals to minus 0.217. Okay. Okay, and next vector as the size vector KB. So in this case, it's the rectangular cross section, right? So its equilibrium diameter equals to 0.808 square root of the H times B, 1 times 2, equal to 1.14 for 3-inch, and this DE is within the range, right? Between the 0.3 and 2. So we use this equation to calculate the KB vector equals to the 0.867. And then it's the loading vector. Well, it's under the actual loading, okay? Actual loading, and the KC equals to the 0.85 and 0.85, 0.85. Okay, so the reliability that we require is the 99%, and the KE vector equals to 0.814, okay, 0.14. Okay, so now we get all those marine vector KA, KC, and the KE. Therefore, the endurance limit in the actual case will equals to those marine vector times the SE prime equals to 25.5 KSI. Okay. Okay, and now we can plot this SN diagram, right? 120, and this high cycle point right here. And here's the endurance limit, SE 25.5. Right? Okay, so we can calculate the A vectors and the B vectors. And we'll plug A and B into the cycle. The function of the linear function, okay, the linear function. A here and B here, right? And the number of cycles that question already tells us is 50,000, right? Therefore, we can find the fatigue strength equals to 45.8 KSI, okay? Okay, so today's course will ended here. Okay, remember that today's course is only talking about the completely reverse stress. That means the mean stress equals to 0. Okay, so the SN diagram is only it can be only used for the completely reversible stress. Okay. Okay, so the course will be ended here. Okay.